and we'll go through these examples much more quickly. B, a high energy molecule. I'm not going to go into the chemical details here, but I'm going to briefly sketch that is an adenosine molecule, which you'll come to know about. And off this adenosine molecule, I'm going to take the phosphate groups that we were just talking about. Negative, 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 negative. That molecule there, hydrophobic or hydrophilic? Hydrophilic. It's very negative, right? Good, but that's not the part I care about. The part I care about is you have 3 phosphate groups. They're all negative. What do negatives like to do? Repel. Do you think those 3 negatives are very happy being covalently bonded to each other? No, they're straining at the bit there. They'd love to get away from each other, right? In other words, if I could free them up, if I could break that bond, I would release energy. It turns out that we can very simply understand here that that is a great way to store energy, and a lot of energy, to use it later to run a reaction. By sticking 3 negatives together, I can store energy. And the cell has figured this out, and it uses that molecule as an energy currency, an energy store to run reactions. When it needs energy, it resorts to adenosine with 3 phosphates, or adenosine triphosphate, or, amongst friends, ATP. There you go. So, last example, and then we'll quit. I just want to bring us back to glycolysis and Buchner and sugars. Let's just talk for a moment about sugars. We'll see more about sugars a little bit later in the course, but let's talk about carbohydrates. Carbohydrates have the following structure. They have a certain number of carbons. I'm going to do a carbohydrate here that has 6 carbons on it. Every carbon except 1 carbon has a hydroxyl group on it, but they can go in different ways in different places and all that. They're on the carbon. I'm drawing this one this way. Just hydrogens there. Except this guy here, or one other one somewhere, we have a carbonyl, C double bond O. And if you do the arithmetic, this thing here, H, I'm bored drawing these H's, and you're going to get bored drawing them, and we're not going to draw them usually, as you'll find out, has this formula CH2O 6 times. That is C6H12O6. If a sugar has 6 carbons, we call it a hexose, because hex means 6. If it has 5 carbons, we call it a pentose, because pent means 5. If it's got 3 carbons, we'll call it a triose, because tri means 3. Anyway, these are just different names for different kinds of sugars. And amongst the hexoses are things like glucose, the very important sugar. In fact, the sugar that yeast needs here in growing, this glucose. Now, I'm not going to go into a lot of detail, but I'm going to mention that this linear chain is not the usual way that glucose will be found. Glucose will spontaneously make itself into a nice little chair. And the structure that glucose is usually running around in looks like this. One of the carbons is up here. Then as we chase the carbon train, carbon, 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 oxygen here, and depending on the sugar, whether these hydroxyl groups are up or down, will vary. And you get this nice thing. And this can be a very reactive group. This monosaccharide, single sugar molecule, they can form together by dehydration synthesis to make two, a disaccharide. And I'm going to forget all the chemical structure here, and I'm just going to draw you a hexagon here and say they might bond together like that. And then they could continue to bond together like that. Or they could bond together in many, many other combinations. Sugars are kind of, very permissive. You can bond them this way and that way and this way. And depending on how you bond them, you get very different shapes. You can make long linear chains that nuzzle up against each other. You can make chains that don't nuzzle up each other. You can make branched structures. And let's just bring up some examples of this. Go. Whoops. Try that again. Oh, yeah, I got it. We can put them together here. You get starch molecules. Put them together in a different way, up, down, up, down, up, down, you get cellulose molecules. You put them together in branched ways, you get what's called glycogen, the way you store sugars in your liver. And in particular, put that guy down there, if we take the way of doing this, where those chains line up just perfectly, whoops. There we go. You do it. Excellent. She's better than me at that. Look what happens. If this lines up just perfectly, you can make hydrogen bonds across and across and across, within and across, and those fibers can be so powerfully strong that you get cellulose that holds up trees. Pretty impressive. And at the same time, by just bonding in a different way, you get the glycogen, which is stored in a completely non-structured, non-rigid way in your liver. So what's the take-home message? If you can bring up our forces, let's go back to bring up our forces. What we've said is life is understandable at a chemical level. We didn't need vitalism to explain life. We got a limited set of forces. We got covalent bonds, strong covalent bonds. We have hydrogen bonds. We've got ionic bonds. We've got van der Waals forces holding up our gecko. We've got hydrophobic forces, which aren't really forces, they're just the exclusion of things that are breaking up happy hydrogen bonds. And together, we can explain, by understanding the structure of a molecule, we can understand how membranes form spontaneously, how energy might be stored in a molecule, how trees might stand up by very large numbers of hydrogen bonds between chains of sugars holding themselves up. At this level, biochemistry helps us understand those things that once seemed magic about life. Next time, we're going to move forward to the most interesting molecule of all, those molecules that Buchner purified from his yeast juice, the proteins that can carry out those magical transformations. So that's for next time. All right, back again with a question. We've got questions for you on carbohydrates and on ATP.